Dear students, welcome to the online class. I am Dr. SSG Hiremat. In this video, you are going to study about the catalysis, energy of activation and steady state approximation. Catalyst is a substance which influences the rate of the reaction and itself remains unchanged at end of the reaction. Catalyst is a substance which influences the rate of a reaction and itself remains unchanged at end of the reaction. Means catalyst increases the rate of the reaction or decreases the rate of the reaction, in total influences the rate of reaction and itself remains unchanged at the end of the reaction. Catalyst increases the rate of reaction by change of the path. Catalyst influences the rate of a reaction by change of path and change of energy of activation. In positive catalysis, energy of activation decreases by the change of path, then more and more number of molecules become eligible to cross the energy barrier and give the product. Now, energy of activation. Energy of activation is the excess energy that the reactant molecules absorb and become activated so that they can give the product. They can give the product. Thus, energy of activation is the excess energy that the reactant molecules absorb and become activated so that they can give the product. Energy of activation may be explained with the help of energy barrier diagram. Here, energy of activation, total energy of activation may be taken as free energy of activation, that is delta G star. It can be explained with the help of energy barrier diagram as follows. Along y-axis energy, along x-axis reaction coordinate, this is the energy level of reactants. This is energy level of products. Then reactants, to transfer into product, they have to cross the barrier in this way. This is activated complex. Uncatalyzed. And for the catalyzed, the barrier becomes lower than in this way. This gives activated complex for catalyzed reaction. And this is the level of energy of activated complex in the case of catalysis, and this is the energy level of activated complex in the case of uncatalyzed. Here, this is the normal molecule. To become the activated complex in the absence of catalyst, it has to absorb this much amount of energy. This energy is represented as delta G. As you know, energy of activation is expressed as the free energy of activation, delta G star for forward reaction. And this is, then another one is the energy, free energy of activation of catalyzed reaction, that is delta G star forward for catalyzed. This is uncatalyzed. Now suppose the same reaction is to be reversed, then this much becomes the energy of activation of backward reaction. It may be represented as delta G star of backward reaction uncatalyzed. Then this is the level of energy of activation or the free energy of activation for catalyzed, delta G star backward reaction, then catalyzed. This is catalyzed. In this way. Here the reactant molecules, in the absence of the catalyst, they have to absorb this much amount of energy to become the activated complex and to give the product. Whereas in the absence of catalyst, only this much amount of energy is absorbed and it forms the activated complex and it can give the product. Thus the energy barrier is decreased by using the catalyst. Similarly, in the case of reverse reaction, when the reactants are converted into products are converted into reactants, the energy barrier, the same is there. Here the energy required in the case of uncatalyzed is this much, whereas in the case of catalyzed is this much. In this way, we can explain the free energy of activation for the catalyzed reaction and uncatalyzed reaction. Here, by using the catalyst, this much free energy of activation is decreased. Thus, the rate of reaction becomes more. Now, what about the total free energy of the reaction? Here, this is the level of energy of the reactants and this is the level of energy of the products. This difference is the free energy of reaction, that is delta G naught, free energy of the reaction. It is same in the case of catalyzed as well as uncatalyzed. Reactants means the energy change of the reaction is the energy of the products minus energy of the reactants. The level of the energy of the reactants and products is unchanged by using the catalyst. Now about the energy of activation expressed in this way. That is, now let us write all these. That is delta G star forward reaction, that is uncat, that is nothing but free energy of activation, for uncatalyzed reaction. Then delta G star forward reaction, uncatalyzed reaction, that is forward reaction. And this is delta G star F, this is for catalyzed reaction, free energy of activation for catalyzed forward reaction. Similarly, we can name for the backward reaction also. Delta G naught is the free energy change free energy change of the reaction. Now, effect of free energy on the rate of the reaction can be explained with the help of the equation which shows the rate constant, that is rate constant of a reaction K forward is equal to KT divided by H e raised to minus delta G star divided by RT for forward reaction. Suppose this is for forward reaction. Then in the case of catalyst, the same may be written as, that is Kf for catalyst equal to KT divided by H e raised to minus delta G star forward, that is catalyzed, divided by RT. Similarly, for uncatalyzed, we may write Kf uncat, that is equal to KT divided by H e raised to minus delta G star forward uncatalyzed divided by RT. In this way, suppose this is general and this is catalyzed and this is for uncatalyzed reaction. Then here Kf are the rate constants and KT bar H is the frequency factor. Equilibrium constant. We can show that by the use of catalyst, equilibrium constant is not altered, but it is achieved in shorter time. It can be shown as follows. Suppose K forward uncat is equal to KT by H e raised to minus delta G star forward uncat divided by RT. Then K backward, that is rate constant for the backward reaction uncat, is equal to KT by H into e raised to minus delta G star for backward reaction uncat divided by RT. Equilibrium constant K is the ratio of rate constants of forward and backward reactions. Therefore, K equilibrium is equal to K forward divided by K backward, that is equal to Kt bar H to e raised to minus delta G star forward divided by Kt divided by H e raised to minus delta T star backward. That is, Kt gets cancelled, then e raised to minus delta G star of forward reaction plus delta G of backward reaction, that is equal to e raised to minus delta G of the forward reaction minus delta G of G star of backward reaction, and this RT remains as it is. This is equal to divided by RT. This is equal to e raised to minus delta G star divided by RT. Delta G star divided by RT. Then this is equal to 6 and this is equal to 7. K equilibrium. Delta G star for catalyzed reaction, delta G naught on G star, delta G naught for catalyzed reaction is equal to the delta G naught for uncatalyzed reaction. Therefore, K equilibrium, that is K equilibrium is not altered by the use of catalyst. Characteristics of catalyst or catalysis. Now, first one, catalyst remains unchanged at end of the reaction. Catalyst does not start or stop the reaction but influences influences the reaction which can take place. Then third one, catalyst is specific in action, means one catalyst is catalyst for the same reaction. Fourth one, catalyst does not alter the equilibrium constant. Equilibrium constant of a reversible reaction. Reversible reaction. Fifth one, for each catalyst there are promoters and catalytic poisons. Steady state approximation. And this is also called the principle. Steady state principle. According to transition state theory, transition state theory, one of the reactant molecule reacts with catalyst or other reactant molecule to form intermediate compound or activated complex. Then activated complex dissociates to give products. Thus, initially activated complex formation goes on increasing and decomposition also goes on increasing. A stage is reached at which rate of formation of intermediate is equal to the rate of decomposition of intermediate. This state is called steady state. It is assumed to be approximately assumed to be steady. Therefore it is called steady state approximation. It is used in calculation of rate constant of a reaction. For example, A is a reactant and C is another reactant or catalyst. They combine to give one intermediate called AC with rate constant K1. The intermediate AC dissociates or decomposes to give the product and liberate the C catalyst or intermediate with rate constant K2. Here rate of formation of AC is equal to K1 into concentration of A into concentration of C, and rate of decomposition of AC is equal to K2 into AC. At steady state, rate of formation of AC is equal to rate of absorption of AC. That is, there is no change in the concentration of AC. That is, d concentration of AC divided by dt is equal to K1 into A into C minus K2 into concentration of AC is equal to 0. That is, there is no change in the concentration of the AC. It is assumed, therefore it is called the approximation. Means at steady state, the change in concentration of the intermediate is taken as equal to 0.